We're now live on YouTube.
Okay, so I should probably refresh. Ah, no, there is waiting time. Yeah. Okay, now I see also the chat.
So are the slides full screen for you?
No.
No? Okay, well, maybe. Like this is maybe better, no?
Yes. So we should, so maybe Harun, you let me know when we should start. Now is 4:03.
At this point, it's absolutely up to you.
There are still people entering the room, so maybe we can wait for another minute. So. Maybe I suggest to start if you agree, Laurent.
As you prefer, Milana, no problem.
So officially welcome everybody to the third Lumer Lecture in this series of the Lumer Lectures, which are organized by our action MAD-VNet, which is actually financially supported by the COST Association. So it's my big pleasure and honor to be the host of this third lecture in front of the Working Group 2 and to introduce our speaker, Professor Laurent Desvillettes from University of Paris in some sense. So let me say a few words about our speaker. So Laurent Desvillettes was a student at the École Normale Supérieure in Paris, and he received his PhD at the University Paris 7 in 1990 under the supervision of Professor Claude Bardos. He became full professor only 4 years after, in 1999, first at the University of Orléans, then École Normale Supérieure de Cachan, and since 2015 at the University Paris Diderot. Now we will see. He provided major contributions about mathematical and numerical properties of PDEs in particular kinetic and reaction diffusion equation with singularities, as much as on their application in fluid mechanics, statistical physics, and population dynamics. So today, Laurent will speak about some aspects of the Landau equation of plasma physics. So Laurent, virtual floor is yours.
Okay, thanks a lot. Thanks a lot for the invitation. So today I would like to say a few things about the so-called Landau equation of plasma physics. Let me add that what I will present has been done in collaboration with two colleagues, both from the Tsinghua University, but it's not the same Tsinghua. So one is in Beijing and the other one is in Taiwan, in fact. So those colleagues are Ling Bing He and Jicheng Jiang. Okay, let me start by saying a few words about maybe one of the most well-known models in statistical physics, namely the Boltzmann equation. And so the operator which appears in the Boltzmann equation was introduced in the mid of the 19th century by Maxwell and Boltzmann, and it describes the evolution of the velocities of a gas which is constituted of monoatomic molecules, like, for example, argon. The idea is that the modification of the velocities can be seen on a function f, which is the density of particles which at a given time has the velocity v. And the idea of both Maxwell and Boltzmann was that the variation of this density f comes from the presence in the gas of collisions between the monoatomic molecules. So the idea underlying the formula which is written on the slide is that you have a molecule of velocity v, and it has a certain probability of meeting a molecule of velocity w. And so in order to represent the effect on the density of velocities, you write the product of f of v and of f of w. And then you multiply that by a certain function, which in fact depends on the relative velocity, which is a modulus of v minus w, and of an angle which has to do with the outgoing relative velocity with respect to the incoming relative velocity. This angle is called theta. So you integrate along all possible partner in a collision, that is all possible w, and all possible angles theta. This gives you the loss term in the Boltzmann operator, which means that it corresponds to the particles which had a velocity v and which, because of a collision, will have a different velocity later. And then you have a gain term, which is written basically in the same way, that is f of w prime, f of v prime times the same function of modulus of velocity and angle. And the w prime and v prime are the velocities that let's say the two molecules have before the collision, and it is in this modeling. The idea is that they will get a velocity, the particle of velocity v prime will get a velocity v after the collision. So then the remark by Maxwell and Boltzmann is that in a monoatomic gas, you don't have any microscopic internal energy in the molecules. And so because of that, during a collision, you preserve both the momentum, the global momentum of the two molecules, and the kinetic energy of the two molecules, which means that you have v prime plus v prime star, which is equal to v plus v star, but also v prime star to the square plus w prime star to the square, plus w prime to the square, sorry, is equal to v to the square plus w to the square. And when you parameterize this manifold, which corresponds to the momenta and kinetic energy which are conserved, you end up with the formulas which are written in the middle of the slide. That is, V prime and V prime star are equal to V plus W divided by 2, which is the velocity of the center of mass of the two molecules, plus and minus a quantity which is identical, and which is this relative velocity V minus W in modulus divided by 2 and multiply by a parameter sigma which lives on the sphere S2. And theta is related to sigma by the fact that the cosine of theta is the scalar product of sigma and of the relative velocity once it has been divided by its modulus. So this is, let's say, the theory of Boltzmann and Maxwell. And the point is that this works basically for collisions between neutral molecules. But if you are interested in collisions between charged particles, which is what happens, for example, in a hot plasma, then you should take into account the fact that in a typical collision between charged particles, the outgoing velocities are very close to the incoming velocities, which means in the parametrization, which is presented here, that the parameter theta is always very small. And so there is this idea that in order to get a good collision operator for charged particles, you should perform the asymptotics of the so-called grazing collisions, which amounts to say that theta is taken very small in the integral here. And if you do that, this means that V prime is very close to V, W prime is very close to W, and you can expand f of W prime, f of V prime minus f of W, f of V in terms of theta. And when you do that, you see that actually there is a first cancellation, which is due to the fact that the collision is grazing. And then the first term which appears is something which is odd with respect to theta, and which disappears in the integral because B depends only on the modulus or on the absolute value of theta. So because of this, you have a second cancellation. And what happens when you do this is that you end up with a term which I write now on this slide, which is called the Landau collision operator, which works for charged particles. And this operator shares a certain number of similarities with the Boltzmann operator. The first one being that it is quadratic with respect to F. And this is related to the fact that you are looking at binary collisions. And the second one is that it is non-local in the sense that you still have the integral with respect to W over R to the 3. What has disappeared is the integral over the angle, because if you remember what I just said, basically we look only at the angles which are extremely small. And so the integral with respect to the angle disappears in the expansion around 0 of the angle. However, what is different from the Boltzmann collision operator is that now you have basically an operator which is second order in terms of derivatives. And you can see that looking at the gradient f of v, which appears in the formula, and the divergence, which is in front of everything. So as you can see, this gives you basically two derivatives in the velocity variable. And the gradient f of w can be, in fact, eliminated by doing an integration by parts in the variable w. So it's like if you had, let's say, a part which is second order and a part which is first order in the equation. Okay. So there is not much to say about the term f of w gradient f of v minus f of v gradient f of w. However, the first thing one thing to say is that it is a vector, okay? And so the idea here is that you apply a matrix which depends on v minus w, which is actually the orthogonal projection onto v minus w orthogonal. So this is a matrix applied to a vector, okay? So it gives you a vector. you multiply it by v minus w to the minus 1, and then you take the divergence. And this is the definition of Landau collision operator for charged particles. So as I said previously, you get this thanks to a formal expansion starting from the Boltzmann equation. And this was written first in a mathematical way, let's say, or in a formal but well-defined way in the book of Chapman and Colling, which is from the 50s. It's interesting to see that actually the operator, which was written before that by Landau in the late 30s, and if you look at the book by Lifshitz and Pitaevsky, which presents the derivation of Landau, it is entirely based on physical consideration and makes no use of the Boltzmann kernel. So it's quite let's say surprising that Landau was able to provide this formula without using the Boltzmann operator at all, because, I mean, as you can see, the formula is rather complicated. Anyway, this operator is used in real numerical computations by people who are working on hot collisional rarefied plasmas. So here all the words are important. So plasmas means that you are looking at a medium in which at least part of the particles are ionized. Hot in this context means that in fact you are in a situation in which most of the particles are ionized, or all of them. Rarefied means that the plasma should not be too dense. And collisional means that you are looking at time scale at which, though the plasma is not very dense, the collisions still have some impact on the evolution of the plasma. So, for example, if you are looking at plasma which are non-magnetized, the typical equation that you would use is the so-called Vlasov-Poisson-Landau equation, which, depending on if you're looking at the ions or the electrons, will write dTf plus v gradient xf. F here depends not only on the velocity variable, but also on time and position. And so dTf plus v gradient xf just is a term which just expresses the fact that you have the inertia of the particle, which is here. So basically, dot x is equal to v, which in terms of PDEs gives you the term v gradient xf. Then you have the effect of the electric field on the particles. This effect is that you modify the velocity thanks to the force which is due to the electric potential. So the electric potential is called phi. The force which is related to this electric potential is gradient phi up to some constant. It is plus or minus gradient phi, depending on the charge of the particles you're looking at. And so you have to add this term in the equation in order to take into account the effect of the electric field. Now, if you put 0 in the right-hand side, this is the Vlasov equation, which was obtained by Vlasov once again, I think it was in the 30s. But if the plasma is collisional, in the sense that the collision plays a role in the evolution of the plasma, then you have to replace 0 by the operator that we just wrote on the previous slide, this Q of FF, this quadratic operator, which is a Landau operator. And all of this is usually coupled by the fact that the potential, the electric potential, is computed thanks to Poisson's law, which is that minus Laplacian phi is equal to the density of charged particles. And more precisely, it is the density in space. So you have to integrate over all possible velocities of the particles, and you end up with this term integral of f of tx v dv. And usually you add some background, which is, for example, if you're looking at the electrons, a row of T and X would be the density of ions, which is supposed given, let's say, in the computation. So as you can see, in real computations, you are in a situation in which the Landau operator is just one of the elements which enter the full system, which is here the Vlasov Poisson Landau system. Let me add that usually one has to add some effect of a magnetic field in order to simulate a plasma. But this is really the kind of equations which are at the base of the numerical simulation of plasmas. Okay, I will not say much more, just to explain the general context where those kind of operators are used. What I would like to present now is a mathematical theory of the Landau operator, which is something which has been developed for, I would say, something like now 30, 40 years. The first mathematical works on the operator were presented, I think, in the 70s. So the first observation is that it's possible to write a nice weak form of the operator. So if you remember, the operator writes like divergence of something. So if you multiply the operator by a test function phi and you integrate over all the possible velocities, the divergence will, you do an integration by part, and the divergence would become the gradient phi that you have at the end of the second line of the computation in the slide. Okay. And you keep all the rest as it is. So now you have the vector f of w gradient f of v minus f of v gradient f of w, and it is better to take its transpose and to put it in front of the matrix. So if you do that, actually the matrix pi of v minus w, which is a projector, acts like a quadratic form on the vector which is on the right, and on the vector gradient phi of v, which is on the vector which is on the left, and the gradient phi of v, which is on the right. Okay. So this is a weak form of the operator, but actually the weak form which is more useful for practical purposes is obtained by adding the change of variable v gives w in this integral. And when you do that, the gradient phi of v becomes gradient phi of v minus gradient phi of w, because the term f of w gradient f of v minus f of v gradient f of w becomes minus itself when v is transformed in w. So you do the half sum of both and you get minus 1/2 of the term which is written in the middle of the slide. And now you see that here, the matrix pi of v minus w acts as a quadratic form on gradient f over f of v minus gradient f over f of w on one side, and gradient phi of v minus gradient phi of w on the other side. So the first consequence of this weak form of the operator is that, as you can immediately see, if you take phi is equal to 1, then you end up with 0. And this means that the integral of q dv is equal to 0, which expresses the conservation of mass of the collision operator. If you take phi of v is equal to vi, if you take phi of v equal to vi, one of the components of the velocity, then the gradient of vi will be a fixed vector. And when you take it in v minus the same quantity in w, it will also give you 0. And this means that the integral of q times vi integrated in v is also equal to 0. This is a conservation of momentum. And finally, if you take phi of v equal to modulus of v to the square divided by 2, its gradient is just v, and you end up with v minus w instead of gradient phi of v minus gradient phi of w. And if you remember that pi is the orthogonal projection onto the orthogonal of V minus W, you also get 0. And finally, you get the conservation of kinetic energy in this computation. Okay, so the weak formulation, which is written here, is the key to understanding the conservation properties of the collision operator. Now, those properties are exactly the same as the conservation properties in the Boltzmann kernel for monoatomic molecules. But there is something more which you can get out of this weak formulation, and this is the entropy structure of the Landau operator. So let me maybe come back to the previous slide. You can see that there is one thing which is natural when you look at the weak formulation. You see that if you are able to replace gradient phi of V by gradient F over F of V, you will have the projection which acts as a quadratic form on the same vector on both sides. Okay, so it's particularly interesting to look at phi in such a way that gradient phi is gradient F over F, which means that gradient phi is gradient of log F, or if you prefer, that phi is log F. So it's quite interesting to take the special case in the weak formulation when you take the function, the test function equal to log F. So if you do that, you take as a test function log F, you end up with a formula which is in the middle of the slide, in which, as you can see, you have the orthogonal projection, which acts on the same vector on the right and on the left. And let's say the orthogonal projection is a semi-definite positive matrix. So this term is non-negative. Actually, it is often useful for mathematical purposes to write it in a slightly different form. This is the line that you have in front of the bigger than 0, in which actually you replace this matrix acting on the two vectors by a cross product of V minus W and of gradient F over F of V minus gradient F over F of W. When you do that, somehow you have V minus W to the minus 2, which appears that you have to put in the formula, which explain why you have minus 3 instead of minus 1 in the exponent on modulus of V minus W. Okay. So to summarize, if you multiply Q of F by log F, and you actually take the minus of this, you obtain something which is positive, and this is called the entropy dissipation of the Landau equation. Actually, if you know well the Boltzmann equation, there is also an entropy dissipation which can be computed, basically with the same kind of arguments. And this one is the limit in the grazing collision limit of the entropy dissipation of the Landau, of the Boltzmann operator. So there is also a link between Boltzmann and Landau at the level of the entropy dissipation. Okay. If you sort of regroup all what we presented up to now, you end up with the following a priori estimate. So now let's look at the, you take the Vlasov Poisson Landau equation that I wrote in the previous slide, and you suppose that F does not depend on X, then all the terms which come from let's say the inertia and the electric field disappear, and you end up with the spatially homogeneous Landau equation, which is just dtF equal to Q of F, where Q is the Landau operator. You add an initial datum, so at time 0, you suppose that the distribution of F respect to V is given and is non-negative. And then you observe that the conservation that we showed and the entropy structure that we defined enables to obtain the following a priori estimate, which is in some sense the structural a priori estimate for the Landau equation, or the physical a priori estimate, if you wish, that if you multiply F by 1 plus v squared over 2, which is basically mass plus kinetic energy, and you integrate in v. This is a quantity which is propagated along the flow of the Landau equation because of the conservation of mass and kinetic energy in the operator. So that's the first thing. The second thing is that if you multiply f by log f, then this corresponds exactly at the level of the right-hand side of the equation of multiplying q of f by log f. And if you integrate that, what we saw is that you end up with a term which is non-negative, okay? And so we called D this term, and in the a priori estimates, this means that if you integrate in time, you will have this term which appears in the right-hand side of the equation. And you can see it as a dissipation. This is the reason why it is called entropy dissipation. The only point one has to be a little careful with here is that actually it is the integral of f log f which gives this term. And here I wrote things in such a way that it is the integral of f, absolute value of log f, which appears. And in fact, one has to work a little to go from the f log f to the f absolute value of log f. But anyway, you can believe me that you end up with this, that this quantity that you have in the middle of the slide is bounded by basically the initial datum, and more precisely, the initial mass, kinetic energy, and entropy of the distribution, the initial distribution F. So from the point of view of physics, what it means is that mass, kinetic energy are conserved. The entropy integral of f log f decreases. The entropy dissipation, which is called D, is bounded in L1 in time, because you can have the integral from 0 to t for any t. And so from the mathematical point of view, what you end up with is basically that f is bounded in L1 with a secant moment, and actually a little more than L1 in the sense that you have a bound in L log L. Plus, you know that the entropy dissipation is bounded in L1 in time. So it is L infinity L1 for L, for F, and it is L1 for D of F. And those are the a priori estimates that you can play with when you're looking at the Landau equation. So starting from this observation, there are a lot of different papers appeared in the last years. Here I have written basically only papers which appeared after 98. There was already a theory existing before that, especially due to Arseniev, Bouriac. So it was a theory coming, let's say, from researchers of the former Soviet Union in the 70s. Let's say the more modern theory started probably in 98 with global weak solutions which were obtained by Villani, and he called them H solutions. But there are also local in-time solutions which were obtained by Alexandre Diaoline and Fournier, very weak solutions which are called renormalized with defect measure, and which work also when f depends on x, which were obtained by Alexandre and Villani in 2004, and smooth solutions which are close to equilibrium. So this is a perturbative theory, which is also in cases in which f depends on x, which were obtained mainly by Guo at the beginning of the 2000s. On my side, I participated somehow in this theory by producing a sort of improvement of the paper by Villani, which I will maybe present a little more in the sequel. But if you look at all of this, the point is that there is no theory existing yet of global strong solutions. That is, either you have global solutions which are weak, or global solutions which start close to an equilibrium, or local solutions which are strong. But you don't have global strong solutions for any any reasonable initial data. So this theory is incomplete. And this is maybe somehow surprising because if you are familiar with parabolic equations, maybe you would prefer to have a presentation of the equation which is less, let's say, a kinetic style and more parabolic style. And in this presentation, it's possible to write the Landau operator as a standard parabolic operator, in the sense that you have divergence of something times gradient f plus something else times f, or gradient f, or yes, something else times f. And the two quantities which are in front of gradient f, and it's maybe the originality of the equation, are things which are convoluted with f. So you still have the non-local aspects, but it is hidden in those two convolutions. Also, it's possible to have a formulation which is even simpler, in which you have A convoluted with f tensor product with the secant gradient of f plus 8 pi f to the square. Here A is a matrix which is completely explicit. Okay. So when you see that, you say, well, it looks very close to the kind of a nonlinear heat equation in which you have a quadratic term appearing in the right hand side, and actually there is very long and precise theory for those things. And so the people who've been looking at the equations, let's say, have identified a certain number of models which have some closeness to the spatially homogeneous Landau equation. The first one, as I tried to convince you, is the nonlinear heat equation in which you have dTf equal Laplacian f plus f square. So actually, it's not very clear if you should compare the Landau equation to this equation in the whole space, or to this equation, let's say, for example, with on the bounded domain with Neumann boundary condition. From my point of view, though formally it looks like the equation is very close to the Landau equation when you look at its aspect, actually among the models that I will present, it is the one which is less close to the Landau equation. And so typically, if you look at this nonlinear heat equation on a bounded space, then you cannot prevent the blow up, because for example, you take data which do not depend on x, then you will just have to solve dTf equal to f square, and you know that it will blow up. Okay. And this is due to the fact that there is no conservation in this equation, whereas we know that there are conserved quantity in the Landau equation. So rather than looking at this kind of nonlinear heat equation, I think it's better to look at the slightly more complicated models which seem to have more to do with the Landau equation. The first one is this so-called quadratic reversible reaction diffusion system, and it's a system which has attracted a lot of interest among specialists of reaction diffusion. It's a situation in which you have, let's say, 4 kinetic components, which you call the A1, A2, A3, A4. And you suppose that you have one chemical reaction, which is like A1 plus A3 gives A2 plus A4, and you suppose that it is reversible. And then you suppose that you are in a chemical reactor in which the components are diffusing with their own rate of diffusion. So on the right-hand side of the equation, you have this heat-like terms, but with different dk. And on the right-hand side, you have this U1, U3 minus U2, U4 with a plus sign for 1 and 3, or 2 and 4, and minus sign for 1 and 3. And so this model is interesting because it has it has conservation, very easy conservation, which is just that if you add the 4 equations and you integrate in X, you see that mass is conserved, basically. And it also has an entropy structure that I will not detail, but for those of you who are familiar with the Boltzmann equation, you can guess that this U1, U4 minus U1, U3 minus U2, U4 can give rise to an entropy structure if you multiply the UK by logarithm of UK, typically. Okay. So there have been a lot of results on this equation, and maybe the 3 last ones, the one by Souplé, Caputo, Goudon, Vasseur, and Fellner, Morgan, Tang, are devoted to prove that there exist, in fact, global strong solutions for this model. So it's not something which is easy to get, but it's true. So if you believe in the analogy between this model and the Landau model, then it gives you hope that maybe there will be global smooth solutions. Some people have been working on a model which looks a little like the nonlinear heat equation, but with a diffusion structure which is slightly different, which is a quadratic itself and non-local in the sense that you put in front of Laplacian f minus Laplacian minus 1 of f. I will not say too much about this. Let's say that this is also interesting to study, and it looks closer to the Landau equation than the standard nonlinear heat equation. But the one I would like to put the focus on is really the familiar 3D incompressible Navier-Stokes equation, in which you have the unknown u, which is now vectorial, and you put the usual term in the incompressible Navier-Stokes equation, that is the convection term u gradient u, which is quadratic, the pressure term gradient p, which you can see as some kind of Lagrange multiplier, and the diffusion term Laplacian u on the right-hand side. And in order to close the equation, you add that the divergence of u equal to 0, which is the incompressibility condition. Okay, so it's interesting, I think, to see that there are obvious similarities between the incompressible 3D Euler Navier-Stokes equation and the spatially homogeneous Landau equation. Those similarities are the fact that they are quadratic, the derivatives are second order, and the dimension is 3. Okay, but in some sense, all those things were also shared by the other models that I presented in the previous slide. If you impose dimension 3. But actually there are a little more, and the presence of projector which appear in the equation, and also there is a very strange link in dimension 2 between the grazing collision asymptotics and the vorticity formulation of not Navier-Stokes but Euler equation, which is something which attracts, let's say, the attention. Anyway, I don't want to say too much about this, but there are, let's say, formal reason to see that those two equations look a little alike. But I would like to emphasize maybe more mathematical points which show that indeed there is some analogy. So the first thing is that you have those conservations. So for Navier-Stokes, it just amounts to say that if you take the integral of the convection plus pressure plus diffusion, you obtain 0, which means that basically the integral of the velocity does not change with time. So for the Landau, we remember that we have conservation of mass, momentum, and energy. So in both equations, you have something which is conserved. And maybe more importantly, there is an entropy or a dissipation structure in both equations. So for the Navier-Stokes, you just use a multiplier u, you multiply the equation by u, and the pressure term and the convection term disappear. And what remains is just the effect of the diffusion term, which is basically u Laplacian u, you integrate by part, and you get this integral of gradient u to the square, which is the dissipation in the Navier-Stokes equation. For Lando, remember that instead of using d over dt of f squared, you will use d over dt of f log f, and you will have this entropy dissipation, which plays the role of the integral of the gradient of u to the square in the Navier-Stokes equation. So both the equation display dissipation structure. But it is clear that from the dissipation structure of the Navier-Stokes equation, you get the immediate a priori estimate that u lies in L infinity with value in L2, and also in L2 with value in H1. Okay, I think it's clear from the equation. You just integrate in time, and you get this. However, for the Landau equation, what it tells you, as I said some time ago, is that for f you end up with the fact that it lies in L infinity with value in L log L. So this is not as good as L infinity with value in L2. And unfortunately, the entropy dissipation part of the estimate does not give you something explicit in terms of Sobolev spaces. What it tells you is that you have this quantity which is complicated, but you know that it is non-negative, which is bounded in L1 in time. So this quantity is the one which is written at the end of the slide. So the point is that it's actually possible to get something in terms of regularity which is more exploitable by working on this quantity, which is the entropy dissipation of Landau. And it's actually what I did in a paper that I wrote a few years ago, which basically tells you the following, that let's say for data which are normalized in the sense of the mass and momentum and the energy are fixed, then it's possible to show that the entropy dissipation of Landau is bounded below, up to a constant, by the quantity that you have on the right-hand side of the last but one line of the slide, where you have this integral of f times gradient f over f to the square times some weight. Now, f times gradient f over f to the square is related to the so-called Fisher information that appears in information theory. You can rewrite it gradient f squared divided by f, or if you prefer, gradient of square root of f to the square. So if you use this last possibility, you see that actually the a priori estimate for the Landau equation can be rewritten quite simply on square root of f. Remember that f was in L infinity with value in L log L. So square root of L will be in L infinity with value in L2 log L2. Okay. Then, because of this theorem that was on the previous slide, you see that square root of f will be in L2 with value in H1 up to a weight. This is a -3, which is written in the slide. And using Sobolev embedding, this will tell you that square root of f is basically in L2 with value in L6 up to a weight. And now this can compare, I think, quite interestingly with what you have in the case of the Navier-Stokes equation, in which you know that u is in L infinity value in L2 and intersected with L2 value in H1. It's what we already saw. And also thanks to a Sobolev embedding, this is also in L2 with value in L6. And as you can see, what you have for square root of f in the case of Lando is very close to what you have for u in the case of incompressible 3D Navier-Stokes. So this is, I think, in some sense, far more convincing than just the fact that you have the same number of derivatives, dimension of the space, or power in the nonlinearity. Actually, it is known since the time of Leray, I think, that for the Navier-Stokes equation, the a priori estimate that you have is enough thanks to some compactness result, which come, for example, from the Aubin-Lyon's lemma, that you have existence of weak solutions for the system. So this was proven, I think, by Leray in the 30s. And for the Landau equation, actually, thanks to this basically the same estimate, except that you have the weights, it's possible, thanks once again to compactness, to show that the terms which appear in the equation are well defined as distribution or L1 function, if you prefer. So this is the key to the existence of standard weak solutions. This improves the theory of H solution, which was proposed by Villani in the 2000s. So basically, thanks to this link between the entropy dissipation and the Fisher information, it is possible to have a good theory of global weak solutions for the Landau equation. But we are still very far from global strong solutions. So let me say that this analogy with the Navier-Stokes equation was used by Gualdani, Goltz, Humbert, and Vasseur very recently to show the equivalent of a classical result on the Navier-Stokes equation, which is a Caffarelli-Kohn-Nirenberg result of the 80s, in which it's possible to show that even though we don't know if blow-up can appear or not for the equation, it's possible to bound the set of times on which the solution is singular. And more precisely, it is the Hausdorff dimension of the set of those times which can be bounded. And so using this link between entropy dissipation and the Fisher information, Gualdani, Goltz, Humbert, and Vasseur were able to get the equivalent for the Landau equation of this Caffarelli-Kohn-Nirenberg theorem. So that is one more reason to believe in this analogy. And now I would like to present the thing that I did together with Jincheng Jiang and Linbing He. And this is based on another classical result on the Navier-Stokes equation, more precisely the 3D incompressible Navier-Stokes equation. So there is this old result by Leray, which says that there is a perturbative theory of strong solutions, which is based on the idea that if in the Navier-Stokes equation you take the product u in L2 times gradient u in L2 small enough, so you suppose this means that the velocity multiplied by its gradient is not too large, then there is indeed a unique strong solutions to the 3D incompressible Navier-Stokes equation. So this is, of course, not a global a theory of global strong solutions for all data, but at least for data which have some smallness, it's possible to show such an existence result. And also in I think it's the same paper, I'm not completely sure. It is proven that now if you take any data as large as you wish, then if you wait for long enough, so after some time which is explicit, some capital T, then the solution will become anyway strong. So in some sense, this means that the diffusion takes over for a time sufficiently large. So those two results are considered as very classical in the Navistox theory. And I would like to present briefly the theorem that Lingbing He and Xincheng Yang did together with me. And it says basically the following: that you take an initial datum which has an entropy, so it is in L log L. It has many moments. Here it is 55, but anyway, we need many moments. And you also suppose that initially it is in H1. Then you can find a certain number of explicit coefficients that I will not detail, such that the following Lyapunov functional exists. So you take the quantity H, which is called the relative entropy, which is integral of F log of F divided by mu minus F plus mu, where mu is the centered reduced Maxwellian. Okay, so this is very close to the entropy. This is called the relative entropy. So you take this quantity, this is called H of t, and then you remove a negative power of the H1 distance between F and the centered reduced Maxwellian to the square, plus some numerical factor. So all of this has a derivative in time, which is negative, and in fact, a little better than negative, because you have some dissipation term, which is C times 1 plus T to the K, along the flow of the Landau equation. So you have a sort of hidden Lyapunov functional in the equation, which makes use of the entropy, which is known as a Lyapunov functional for a very long time, but which also uses some other quantities which are related to the H1 norm, let's say, of F. Now it looks like it's very difficult to use this information, because H minus this quantity is something which has no sign. So it's not so easy to deduce from this an a priori estimate. But by working a little, it is possible to show that, provided that the initial entropy times some power of basically the H1 norm of F at time 0. So if this quantity is small enough, and this is explicit, here it's 5/2, then actually there will exist a global and strong solution of the Landau equation forever. So this is an analogic to the result of Leray on the Navier-Stokes equation, which tells you that if U in L2 times gradient U in L2 is small enough, then you have global strong solutions. As you can see here, in some sense, the L2 norm of U is replaced by the entropy, which makes sense because it's the quantity which is dissipated. And the H1 norm of U is replaced by something which makes use of the H1 norm of F. So it looks slightly similar, let's say. So that's the first part, let's say, of the first use of this new entropy functional, this new Lyapunov functional. And the second one is also analogic to what happens for the Navier-Stokes equation. It tells you that now, if you suppose that the initial datum is not such that this quantity is less than 5/2, so let's suppose it's bigger, then if you wait long enough, you will find an explicit time, which is given by a formula, such that after this time, the solution of the Landau equation is indeed still global and strong. So somehow we have now a situation in which we have one more result, which is known on the Navier-Stokes equation, which can be proven on the Landau equation. So I hope that I have convinced you that there is indeed a strong analogy between the two equations. Maybe I will stop here for the technical part. I will just say one or two words about what we are trying to do now on this problem. The first thing is that the result of Leray has been improved, and as you know, many people are working on the incompressible Navier-Stokes equation. So there are many mathematical results now, and let's say the product between the L2 norm of U and the H1 norm of U can be replaced somehow by some H1 half norm of U. And we still don't know how to do that at the level of the Landau equation. So that is one thing that we would like to know. Also, among the works on the Navier-Stokes equation, some of them are very interesting in the sense that they cannot tell you that blow-up does not exist, but they tell you that if blow-up exists, then there are a certain number of constraints on the way this blow-up develops. So there are many results like that. And one of the things that we would like to do is to get such a description of a possible blow-up. And up to now, we have very rough estimates. And our hope is that we can get so-called algebraic estimates in the case of blow-up. So those two things, let's say, are directly related to things which are known on the Navier-Stokes and that we hope to prove on the Landau. The last thing, which is written in the middle of the slide, is the fact that in the proof, we use the Lorentz spaces, which are not so easy to manipulate. And our hope is that they can be eliminated maybe by a better proof. So those are three directions in which we are looking now. Let me maybe end the talk by saying that it looks like the specially homogeneous Landau equation in some sense is harder to solve than the incompressible 3D Navier-Stokes equation, which itself is very hard to solve. And it's one of the millennial problems. And so there is not a lot of hope for proving existence of global strong solutions for the Landau, if you think of it in this way. But it's maybe not the right way to think of it. And actually, it's not really sure that the Landau is more complicated or more difficult than the incompressible Navier-Stokes. It's not so clear. And I would like to say that maybe this can be seen on this slide that I presented, this one. The model for the quadratic reversible reaction diffusion system for up to 2 years ago, 3 years ago, was considered as, let's say, completely open, and it was not clear if it were easier or more difficult than the 3D incompressible Navier-Stokes. And finally, there were 3 papers with 3 different methods which were able to prove global existence of strong solutions. So maybe this will also happen for the Landau equation, and maybe in the end we will see that it is much easier than the incompressible Navier-Stokes. Who knows? So I will finish with this remark.
Thank you. So I think at this point we can open the question session. So are there any questions? You can, I think, either post in chat so I can read it, or you can simply unmute yourself and just speak. Yeah, Delio.
Thank you very much for this beautiful talk. It was really very inspiring. I'm certainly not an expert in Landau equation, not even in Navier-Stokes, but I was wondering, I mean, for Navier-Stokes, there is, as far as I know, a good theory also concerning equation on domains and boundary conditions. So is there anything similar for Landau? And second question, I was very fascinated by this eventual smoothness of your solution. So after a certain time, you have strong solution. Can you estimate T, and can you think, if there is a good theory also for domains, can you think that this T may depend on geometry of this domain where the Landau equation is living?
Okay, so for the first part of the question, that is is it meaningful, let's say, to consider, for example, a bounded domain My feeling is that here we are dealing with a space of velocities, not the usual space. So it's not so clear to find cases in which let's say the whole space of velocities could be replaced by a bounded domain. Actually, there is a special relativistic version of the equation in which, of course, the velocity will live in the velocity less than speed of light. But the equation is slightly different. So it's not just adding a boundary. Also, there may be versions of the equations in which you look at semiconductors or things like that, and then you are in some Brillouin zone, and you are closer, let's say, to something which would be some kind of periodic setting. But once again, it will not be exactly the same equation. So for exactly this equation, I don't think that that this is meaningful to try to get it outside of R3. So for the second part of the question, so the point is that you're right that the time at which you know that the solution becomes smooth is something which can indeed be estimated. I mean, there is an explicit formula which tells you that after this time, it works. Of course, it does not tell you exactly the time at which it works, but it gives you an estimate of it. And as long as we don't have examples of blowups, we cannot bound it from below in some sense. So we only have this estimate. So then, for example, it would be interesting to try to do the same for the special relativistic equation. Actually, this is something which has been looked a little, I think, by Bob Strain from University of Pennsylvania. But I mean, even writing the special relativistic equation is no fun.
Okay, thanks.
Thank you. So Jan Gieselman.
Yeah, thank you for the very nice talk. I was wondering about this theorem also, where you show that solutions of the Landau equations become smooth after some time, and you say that a weak solution can be constructed. So do I understand it correctly that there are several weak solutions? And if the answer to that is yes, is the solution that becomes smooth somehow a special weak solution that has some nice properties, or is it just something you can construct in some more or less explicit way?
No, you're right. There is an issue with uniqueness with that. So the conjecture would be that there is uniqueness for this equation, and so hopefully there is only one weak solution, and it becomes strong after some time. So that is a conjecture. Now, what is proven is that actually there is one weak solution which becomes strong after some time. So this is what is proven. And basically, in some sense, it becomes strong as soon as it can be constructed by an explicit approximation scheme. This is another way of saying it, that if you have a good approximation scheme, then you will construct a solution which will become strong after some time. But we cannot completely rule out the possibility that there is some strange weak solution which cannot be obtained by an approximation procedure and which would not become strong.
Yeah. Are you thinking or you have
Yeah, thank you for the answer. Yes, I'm thinking about the answer, and I'm thinking about what I know about weak solutions of the Navier-Stokes equations, because I mean, apparently that is a good guideline to understand what is going on here, but I don't want to stop the discussion. So I mean, other people should ask questions, I guess.
Thank you. So do we have other questions, maybe? I will also see the YouTube. Okay, maybe I have one philosophical question. I think going back to discussion from some years ago. So the very, I think, second slide, when you show this grazing limit, so you start with the Boltzmann operator, go to Landau. So, and then if you go to the system of Boltzmann equations, is there, how it goes? I mean, what will be the spirit?
Yeah, that's actually that's an interesting question. I think it's not so easy to answer that. I mean, my feeling is that from the mathematical point of view, you can start from a system of Boltzmann equation for different species, let's say, and do the grazing collision asymptotics, and you will get a system of Landau equations for different species. This I'm sure. But I'm not sure that this makes sense from the point of view of physics. Because the typical situation that you have in plasmas is that you have, on one hand, ions, and you can have many different species of ions. And on the other hand, you have electrons. And the ratio of mass between those two things is at least 1/2000, I think. I mean, even if you have very, very small ions, they will weigh like more than 1,000 the weight of an electron. And so in this situation, the grazing collision asymptotics does not look really meaningful, because you also have to do something about the masses. And so this is probably one of the reasons why people using these equations in the context of plasmas, for example, sometimes they suppose that the electrons are already thermalized, so they are given by a Maxwellian, which is given, and then you look at the Landau equation only for the ions. So you see what I mean? I mean, in some sense, I think that the good asymptotics from the point of view of physics are probably more complicated and certainly involve the mass ratios.
Yeah, and maybe different recombinations and so on, yeah. So I can ask once more, are there any, yeah, okay.
I have one question.
Yeah, please.
Yes, it's related to the potential. You use Coulombic potential.
Sure.
But but if the potential is much better, you have maybe you can prove that there is a strong solution. If there is not such a
yes, sure. So the situation, if I'm not mistaken, is that the strong solution exists for moderately soft potential up to -2. So Coulomb being -3 in this, if you think of it.
So this is like a dimension that you cannot see in the Navistox equation. If this convolution with
so my feeling, maybe I'm mistaken, but my feeling is that maybe the Coulomb case is the one which is the most analogic to Navistox. But I cannot really prove that seriously, of course. But that would be my feeling. Anyway, it's in the work with Lingbing and Jingqiang, it looks like the Coulomb case is really borderline. Whereas when you look for strong solutions directly, it looks like it's the borderline is -2, and you're still far from Coulomb.
So there is this range that that is unclear.
Exactly. And even the case exactly -2, I've never really completely understood the proof. There is one proof, but it's more difficult than what I know how to do.
Okay. Some other questions, maybe?
Yeah, if I may, I would ask a follow-up question on my last question.
Sure.
So my impression was that for incompressible Euler, for incompressible Navier-Stokes, there are some notions of weak solutions where you do not have uniqueness, and there are some notions of weak solutions where you hope to have uniqueness. And you said that you expect that for the equations at hand, you would conjecture that weak solutions are unique. So what is the reason for this optimism?
Yeah, actually, if I'm not mistaken, the non-uniqueness is more for the Euler, for the incompressible Euler, if I'm not mistaken.
Yeah, I was just looking at a paper of Bookmaster and Vicol, and they really say that at least in convex integration, it depends on whether you look at distributional weak solutions or Leray-Hopf weak solutions. Okay,
so no, I didn't know that you also had a counterexample in Navier-Stokes' case. But actually, I may have sounded optimistic. I'm not that much. So actually the only result on uniqueness which is meaningful for that kind of solutions is something which was proven a few years ago, I think by Fournier, and it says somehow that it's enough to know that, of course, uniqueness related to regularity, let's say, and the regularity that enables you to get uniqueness is, if I'm not mistaken, L1 in time, L infinity in V. So with the solution that we have now, we are very far from that. We have basically L1 in time, L3 in V. So I'm not that optimistic actually, but let's say I think that the conjecture would be that there is some uniqueness result. I don't think people expect bad behavior, but maybe I mean the main difference probably with the equations of fluid mechanics is that for the equation of fluid mechanics, people have been looking a lot and have worked so much. Which is of course not the case for this equation of kinetic theory. So it's not a big surprise that you have more strange results and more exciting results in fluid mechanics. So many people working on that, and I mean all these strange result of non-uniqueness or of let's say compact supported in time solutions and things like that. It's something that does not yet exist, I would say, in especially homogeneous kinetic theory.
Okay, thank you.
Thank you. And there is a message in chat. I don't know if you can, yeah, I can read it. So there is, so Andrea Bondesan wrote that there is actually a very recent result of Maria Colombo and co-authors that shows non-uniqueness.
Yeah. So it's in the same direction that Andrea points out. But yeah. Those results sort of seem to crop up in fluid mechanics. I mean, there are so many strange solutions and so many non-uniqueness and yeah.
Okay. So some more questions? The last call. Okay, if not, thank you, Laurent, for the great talk. And
Thanks a lot.
So I will do it in the classical way. And with this, I think, yeah, we can close this Lumer lecture, the third one. And we expect the next one in about, I think, 2 months. So thank you, everyone, also for joining. And thank you, Laurent, once again, really, for accepting the invitation to give a lecture.
Thanks to all of you.
Okay. Bye.
Bye-bye.